Hello folks. Hope you all are doing well. Welcome to one new video. And in this video, we are going to understand how internally the data type that we are using is stored in a memory. So basically, our next lesson is all about understanding bitwise operations. So it's a bit important to understand how numbers are actually represented as bits. So that's why I thought of kind of having a quick bonus lecture before we actually proceed to how bitwise operations work. So without any delay, let's quickly jump in. So what you see here seems a bit intimidating, isn't it? So if you just follow along with me, you should be fine. So basically what you see over here is how we are converting between a decimal number to a binary number. So normally when we store a number, we think in terms of decimal, but how the computer stores it internally is in the binary system. So it is imperative for us to understand how to convert a decimal number to a binary representation, and from binary how we can get back the same decimal number. So let's say I have a decimal number 10 and I want to convert it into binary. How we are going to do that? So basically keep on dividing 10 by 2, and every step keep a tab of the remainder. So if I divide 10 by 2, the remainder of that step is 0. If I divide 5 by 2, remainder is 1. 2 by 2, it is 0. And 1 by 2, it is 1. So once the division is complete, we will read from bottom to the top and then keep on writing the bits. So whatever we took from the bottom goes in the leftmost position and then followed by the next subsequent bits towards the rightmost position. So 10 after being converted to binary is 1010. Next, what we are going to see is how do we know that this binary number represents a decimal 10? So for that, you need to know the reverse process, how to convert a binary number into a decimal number. So for that, I have written the number as it is 1010, as you can see here, and then padded it with zeros to make it a 8-bit representation. As you can see, it's a 8-bit. There are 8 numbers, binary numbers, which you see here. So it's a 8-bit representation. Now, basically what happens is, starting from the most significant bit is the leftmost bit of a binary representation. So this is the most significant bit, and the rightmost bit is the least significant bit. So this one is the least significant bit. So what is least significant bit? It contributes the smallest amount of value to a particular number, and most significant bit is, if that bit is turned on, it contributes a higher value than a lower significant bit can do. So here how that happens, we'll see that next. So starting from right to left, you keep on adding powers of 2. So 2 to the power of 0 is the value that the most significant bit will contribute to the number. Then moving on to the next leftmost bit is 2 to the power 1. Then we go in this fashion, 2 to the power 2, 2 to the power 3, up to 2 to the power 8. Okay. So if you follow this fashion, you will see that each of these bit position has a particular value that it contributes to the number. So this particular bit, the least significant bit, contributes 1. Then the one left of that contributes a 2. Then this bit contributes a 4. Then this next bit contributes a 8. So how we are getting this 8 is 2 to the power 3 is 8. How we are getting this 16? 2 to the power 4 is 16. How we are getting 32? 2 to the power is 32. So you get that, right? You get the flow, how this is working. So now, how do I know that this number that we found for 10 represents a 10? So we will see what are the value of the bit positions which are having a 1 in them. So you can see only 2 positions in this entire number is having a 1. And what is the corresponding value of this position? So for this one, we see a 2, and for this one, we see a 8. If we add 8 plus 2, we are getting a 10. So that is how we are representing a decimal number in a binary system. We by now should have understood how we have converted a decimal number to a binary number and from binary to decimal. Next, we are going to understand what is 1's and 2's complement. We will see what is the use of 1's and 2's complement in a future section of this tutorial. So let's first understand how to calculate the 1's complement and 2's complement. So for that, we will have a decimal number, let's say 15, and we represent it in binary. Take this as an exercise. Try to work it out yourself, and you will get this kind of representation, right? So if we want to know that how we got this representation, just tally it with this particular example. So here you see the last 4 bits are set. So the value of the last 4 bits are 8, 4, 2 and 1. If you sum 8, 4, 2 and 1, you will get 15. So that's why 15 is represented like this. Next, coming to 1's complement. In 1's complement, what we do is we basically toggle all the bits which are there in a number. So basically 1 will become a 0 and 0 will become a 1. So if you do that to this particular representation, you will get 1, 1, 1, 1, 0, 0, 0, 0. Next, how to calculate 2's complement? In 2's complement, starting from the least significant bit, we go to the first non-zero bit, leave it as it is. Then we toggle every other bit after that position. So in this above example, if we start from the least significant bit, we keep on going till the first set bit. So I go to 0, then I move to this 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 1. Once I reach this 1, I will use that 1 as it is. I will not change its value. So that's why you see that 1 is copied below here. Then after that, till the most significant bit, we will toggle all the digits. So if it's a 1, it will become a 0. If it's a 0, it will become a 1. So following that representation, we will see that we will get this kind of representation for 15. This next section, we are going to see how we are storing an actual integer in its 32-bit data type. So let's say 15 is there. 15 will be stored in 32 bits. So what you see here is 32-bit or 4 byte of memory with the last 4 bits already set. Why the last 4 bits are set? Because we are representing 15 and last 4 bit positions value are 8, 4, 2 and 1. So if you sum them up, you are going to get 15. Apart from that, all other bits are not set. So everything is 0. So now that is for positive 15. What about negative 15? Negative 15 is stored in a 2's complement format. If it's a positive number, we store the number as it is. There is no 2's complement, 1's complement for positive numbers. But negative numbers are stored in 2's complement format. And why is that? We will see that as well. So first we will see how a negative number is represented. So if you do a 2's complement of this 15 in the way we just saw in this section, so keeping the least significant one as it is, we are going to toggle all other bits. So here you can see the least significant one is the first position itself. So I have not toggled it. I have kept it as it is. Then whatever value is there, I have kept on toggling. So all the 3 ones you see here, right, has been turned into zeros, and all these zeros have been turned into ones. So that is how we are representing a negative 15. And one more thing is Java uses signed integers. Signed integers uses the most significant bit which is there in the number to keep a tab of the sign. So if it is a 0, that means it is a positive number. If it is a minus, if it's a 1, that means it's a negative number. So once we do 15's 2's complement, we see that the most significant bit is set to 1. So that means it is a negative representation. And this entire number is a huge number. If you do the calculation normally using the technique that we just learned, it will be some huge number. But that is how minus 15 is getting stored internally. Now, why do we store negative numbers in the form of a 2's complement? So that will become evident in this next example. So if we add 15 and minus 15, what we will get? Normally, if you do the maths, it will come to 0. So let's see if I add these two notations that we have internally, is it resulting in 0 or not? So I write the notation for positive 15 first, which has been copied as it is here. Next, minus 15, we have also copied this 2's complement notation here. So if you are not familiar with binary arithmetic, if there is a 1 and a 0, it results in a 1. If it's a 1 and a 1, it results in a 2, which is represented as 1 and 0 in binary. So we write the 0 here and we carry over a 1. And if we add 0 and 0, obviously the result is a 0. So 1 plus 1 should be a 0 with a 1 carryover. 1 plus 0 is a 1 and 0 plus 0 is a 0. Just keep that in mind while we do this calculation. So we see we are adding 1 and 1, so it becomes a 0 and we have a carryover 1. So again, with the carryover 1 and this 1, again it is a 0. Again for this also it is a 0. Again for this also a 0. And here also we are getting 1 as well. And like that, you see all the bits that carry forward 1 is going to get propagated till the last, and all of them will become a 0. So the final value that we are going to get is a 0. So you see, that is the magic. That is why 2's complement representation is in place. Because when we are subtracting also, we can use the additive math to get the subtraction result as well. So there is no need for a specific logical circuit or specific logical design for subtraction and that for addition. So all the operation, whether it is subtraction or addition, can be achieved just with addition if we just store the number in a specific format. So for positive numbers, we use the normal representation, and for negative numbers, we store it in such a way that if we perform addition of the number, we are going to get the subtracted result that you have seen in this case. So now, based on the things that we have learned so far, we will see how we have calculated the max and minimum possible values for a particular data type. So if you remember in one of our previous lectures, we were giving you the ranges, the maximum and minimum values that we are able to store in a particular integer or a floating point data type, right? So how that is done. So I'll just demonstrate quickly to you how that is done for integers. So integer is a 4-byte data type. That means there are 32 bits. So let's say I want to store the maximum possible value in that, right? So what we can do is, we already know we cannot store any value in the most significant bit position because that is indicative of the sign of the number, whether it is positive or negative. So we have actually 31 bits to form our largest number. So how we can do? We have to turn on all the bit positions, all the 31 bit positions to get the maximum number. So as you can see, the max of an integer is, we can't store any value here because this is for sign. And apart from this, all the 31 bits, each of them are set to 1. So whatever is the positional value for each of these bits, right, that gets added and we get the maximum possible result, which is 7FFFFFFF. So don't get confused about what F is. F is called a hexadecimal number. So hexadecimal number are composed of 4 bits. So as you can see here, F is represented as 1111. So if you do the math, 8 plus 4 plus 2 plus 1, it's a 15. So 15 decimal is represented as F in hexadecimal. So hexadecimal numbers are from 0 to 9 and then from A to F. A is 10, B is 11 and F is 15. Okay. Now 7 is represented as 0, 1, 1, 1. How? If you add 4 and 2 and 1, you are going to get a 7. And 8 is represented as 1, 0, 0, 0. So 1 is here 8 and 0, 0, 0 means no other bit is set. So I'll only get the value of 8, right? So the maximum possible integer that is possible to store here is 7FFFFFF. So we see over here a number line. So normally we will see positive values represented towards the right side and negative values towards the left. But here it is the opposite. So we have taken positive values towards the left and negative values towards the right. So let's say the maximum positive value is 7 and FFF. So what will happen if we want the next higher number, right? So there will be an overflow because the data type range does not support such a big value. So what will happen is whenever we are adding a 1 to the maximum possible value, we will get the minimum possible or the minimum value that this particular data type can store. So going with that particular logic in mind, so this is the maximum number for 32 bits. So if we add a 1 to this particular number, we will get the minimum possible value as well. So if you add 1 to this number, what you are going to get is what we are seeing below. So only the most significant bit will be a 1 and rest of all the bits will be turned off. So this is basically in hexadecimal, we represent this number as 8 and 7 zeros. So that is the minimum possible value that we can store. This is also known as -0 because if you do a 2's complement of -0, this is the number that you are going to get. Since 0 is included twice, so let's say when we are going for the max range, we start off from a +0 and we go to the max. And when we are writing numbers from 0 to the minimum possible value, we again include one more 0. So 0 is normally included twice. So basically we have to subtract one value from the complement of this number, and then that will give us the minimum possible value. So that brings us to end of this lesson. Hopefully you had fun and kind of you grabbed the concepts for this particular session. This is going to prove really helpful once we start discussing the shift operators, the bitwise operators, how they work at the bit level. So thank you. Thanks for your time. Thanks for watching. And don't forget to like and subscribe and hit the bell notification. And see you in the next video. Until then, bye-bye.